Hey everybody, we are in our last little installment for the section 1.2. We're going to talk about some symmetry. So there are two different types of symmetry that we're going to really focus on, which are even and odd. You'll be able to know if a function is even if you know that if you were to plug in a negative x, it comes out as the same thing as your f of x function. Another way is if you were to graph it and you see that it's symmetrical across the y-axis. That's a graphical way to see it, but we don't always have the ability to graph things quickly. Sometimes it's more efficient to do it with algebra. So with algebra, you would plug in a negative x, see if you get the same thing as that f of x. If not, then we would go and we'd check and see if it was odd. An odd function is going to have that f of negative x, but it will be equal to negative f of x. So it would just take one extra little step. Another way to do it is to see if it's symmetrical about the origin, meaning 180-degree rotation. Does it look the same right side up as it does upside down? If that's the case, then it is odd. But again, we don't always have the ability to use graphing stuff, so we have the algebraic way that we're going to focus on here. Okay? So we have three problems. If you want to pause the video and write them down, feel free. I'm going to switch us over to the paper that I'm going to write on. Okay? So you can tell I kind of had a hard time writing these things. I kept writing the wrong letters. Anyways, all right, it's asking if it's even, odd, or neither. So for each one of these, I'm going to start off by looking at what is f of negative x. Well, the way that I determine that is I just look wherever I have an x, and we're going to put a negative x instead. So I want you to look here. If I were to take this negative x and square it, negative times negative is a positive, all right? We get this x squared minus 3. So I want you to look. F of x was x squared minus 3. F of negative x is also x squared minus 3. So we do have a situation where our f of x does in fact equal f of negative x. Okay? And because that's the case, that means that f is even. So we're going to say, therefore, f is even. Done. All right, look at B. We're going to do the same thing. I'm going to start with the negative x version and see what we get. So I'm going to look here and look at wherever I have an x, we're going to put negative x instead. Okay, there we are. We're going to work through this, make it a little bit cleaner. Negative x squared is going to be a positive x squared. We have a negative 2 times a negative x, which makes a positive 2x, and we have minus 2. So this is not exactly matching up my original g function. The big difference here is these signs, okay? But that is enough to say that those don't match. So it's not even. But we can then check and see, is it odd? So the next thing I'm going to do is I'm going to check, what about negative g of x? That would be me taking the g function and multiplying the whole thing by a negative, right? Okay, well, if I do that, I get negative x squared plus 2x plus 2, which does not match the negative x. Remember how we said that if it was going to be odd, it was going to have the g of negative x be equal to negative g of x. It's not the same. So because we don't have, right, g of x is not equal to g of negative x, and that is also not equal to negative g of x, that means it's not either one. We're going to say g is neither. All right? So we had even, we have neither. You can probably guess what this last one's going to be, but let's work through it, make sure that we see. All right, so we're going to check first and see, what about h of negative x? That means wherever you put an x, we're going to put a negative x instead. So we're going to put a negative x, that's going to be cubed, up there in the top, divided by 4 minus negative x squared. Well, negative x cubed, if you do a negative times a negative times a negative, so you have 3, that's going to give you a negative x. So that's still negative x cubed. Down here, we get a negative x squared is going to be a positive x squared. So we have 4 minus x squared. So this is not matching the original h function because that top number is a negative instead of a positive. So then let's check and see, what about negative h? That would be me taking this function and multiplying by a negative. So I'd be doing a negative times x cubed over 4 minus x squared. It's the same type of thing as taking a negative 1 over 1, okay, if that helps you see it. I would be multiplying that through. That negative 1 times x cubed would be a negative x cubed over, and then we have 4 minus x squared. So I want you to look at this. This piece right here matches this one. So we do see that h of negative x equals negative h of x. And because those are equal, we say therefore h is odd. Okay? Okay, so that's even, odd, or neither. Now again, I'm going to show you real quick what we mean with this symmetry thing. I only have one of these loaded in my calculator, but if you look at that original, that first one, I put in here x squared minus 3. I want you to see what I mean by symmetry across the y-axis. If I graph this, this is the same on either side of the y-axis, right? It's like a mirror image. You could fold it on that line and it would, or just flip it across that line and you would get the same graph back. So that's what we mean by symmetry across the y-axis. And what we mean with odd is if you were going to graph this odd function, it will look the same upside down as it does right side up. All right, let's talk about continuity. Continuity, there are different ways to check for continuity. There's continuous, which means that a function has no break in the graph. There's no holes, there's no asymptotes, nothing. There's no jumps. It's just continuous. So you're seeing that as your first graph here. It never stops. It just continues to go on either side and it doesn't have a break, okay? But if you look at, we have discontinuity. There's 3 of them here that we're going to show, okay? So there's removable discontinuity to where there's a little hole in your graph, okay? Now sometimes that hole might have it might end up having a point somewhere along, along that same x value, somewhere randomly off of the graph. But what we're looking at with removable discontinuity is you're seeing a hole in your graph. It's looking like it's mostly continuous except for that one spot. Okay, so I don't know if y'all can see very well. Yeah, but you should see that that is open. Okay, now jump discontinuity is where you have this function and then it appears to jump to a different location and then start going from there. So that's jump discontinuity. And then infinite discontinuity means that we have an asymptote. Okay, so here we see a vertical asymptote, which is that break in your graph, and it will never touch that x value. Okay, so cool. That's continuity, and that's a pretty big idea, but it seems pretty basic until we start getting into all the nitty-gritty of it. Okay, so here we're going to talk about asymptotes. Now you guys should have learned some about asymptotes in the past, but we're going to have a slightly different notation that we're going to learn how to use. This is the type of notation that they like us to use for this pre-calculus course. And so you're going to see here, okay, about horizontal asymptotes. All right. Horizontal asymptotes talk about having a horizontal line. Okay, I'm trying to mime it. A horizontal line that your graph approaches, but it may not necessarily meet. Now, in some cases, it can actually kind of cross a horizontal one, but in all those situations, a horizontal asymptote will also be a place where part of the graph may approach but not actually hit. Okay, now there's this notation that we have. And what we're saying here, okay, before we get into the notation too much, let's talk about this wording. okay, this horizontal asymptote, we'd say y equals b, whatever that value is when it's approaching, okay? If your f of x function, if it approaches that value, so it doesn't necessarily meet it, but it approaches it as your x approaches positive infinity or negative infinity. So as your graph goes to the left and the right for forever, that's what that means. As your graph goes to the left and right for forever, it's slowly and slowly approaching this value of y, okay? Now this notation is just a way to notate what we just said. It just says that you have this limit, okay? It has this limit that it's going to reach. It doesn't necessarily reach it, right? It is approaching that value, and that is the limit that it could possibly, that it's approaching. So we're saying a limit as x approaches negative infinity, so as it goes to the left on your graph for forever, then it's going towards this value. And over here, this is as your x approaches positive infinity, as it goes to the right for forever, your graph is approaching this value, okay? And a vertical asymptote, we're going to use some limit notation for that as well. Same idea, we have this value, it's approaching this, but this time it's the x value because it's a vertical asymptote, okay? So because of that, we're saying x equals a is a vertical asymptote of f if the f of x function, right, approaches a limit of positive or negative infinity as your x approaches a from either direction. So here we would be saying the limit as x approaches a, and you see that little minus, it means from the left. So as your function approaches this value of x from the left side, it's going towards positive or negative infinity. Or as it's approaching it from the right side, it's approaching positive or negative infinity. So I know it's a little bit weird. You will get used to it, but that's kind of the notation we're going with. And guys, this is the last example we're going to go through for this unit. Okay, so if you want to pause the video and write that down, feel free. You also will probably want to have a graphing calculator handy so that you can type it in, because it's going to be helpful to be able to see our graph. Okay. All right, here we are with this. I'm going to start typing this in here. I don't have it yet because I just had the other function. So just take a moment, get it typed. Okay. All right, let's look at what this looks like. It looks pretty crazy. Okay, I'm going to get a little sketch going here just so I can write on it. So we have this situation. We have this situation. And we have that one, something like that. Okay, so what's coming to my head, right? Not lovely. Okay, so what's coming to my head when I see this is I'm seeing three asymptotes. There's these vertical ones, which I feel like are the most obvious, okay? But I also see this place here. Do you see how as the graph is going towards positive infinity, it's reaching this x-axis, but it's not actually hitting it? Look at from on the left side, as it's going to the left for forever, it's still approaching that x-axis, but it's not actually meeting it. So that tells me that there's a little horizontal asymptote there as well. So I'm seeing three. However, we're going to make sure that we see how you can calculate for those. So one way that you can find vertical asymptotes is you can look for wherever is going to make your denominator equal to 0. So if you were to solve that, you could take this x squared minus x minus 2, solve that for 0, because that would tell you where your denominator is 0. Let's see, does that factor x and x? 1 and 2, negative, positive. Yes, it does. So we're looking at where x is negative 1 and where x is a positive 2. Those are these asymptotes. Okay? So my vertical asymptotes, I'm just going to abbreviate there, but that's going to be at x equals negative 1 and x equals 2. Those are these values that it's reaching. Now, The reason is, okay, because as we're looking at this graph, okay, as our x's approach this -1, so look here, this is supposed to be the value x equals -1. Here, this is supposed to be x equals 2, okay? As x is approaching this -1 dashed line, okay, do you see how the graph is going up, 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 up forever? It's never stopping. So because we have a limit, because as our x is approaching that -1 from the left, okay, so this is from the left. Oops, sorry, no, this is from the left. You're lying. Gotta know my left and right, huh? As it's approaching from the left, it's gonna be going down for forever. And as it's approaching that from the right, it's going up for forever. So I'm gonna say as it's approaching from the left, we're gonna say that my f of x function is going towards -infinity, because as it's approaching this from the left, it's going down forever. And again, as it's going from the right, it's going up for forever. Okay, so that's for this asymptote. But look at this next one. This one is because as my function approaches to, let's say from the left, so we're staying consistent. As it's approaching this from the left, it's going down. So it's going towards -infinity. Okay, and then the other one, as it's approaching, x approaches 2 from the right, look at this, it's going up for forever. So this is positive infinity. All right, so those are your vertical asymptotes, but my horizontal asymptote, I want you to look at this. Okay, and this is my last one. My horizontal asymptote. Okay, and that's going to be at y equals 0. We can see it here. And the reason is because as my function approaches -infinity, as my graph goes to the left for forever, okay, as it approaches -infinity, the graph is getting closer and closer and closer to that y value 0. Okay, but also look on the other side. As we get closer and closer, or as we go to the right for forever and always, it's getting closer and closer and closer to that y value 0. So on both sides, it is approaching that same thing. It's getting closer and closer and closer to that asymptote, but it will never actually reach it. Yes, it does cross it in the middle. That is a number one concern a lot of people will ask about, and that is that's okay. It can, horizontal asymptotes can cross at some point, but you're looking at it as the x is going to the left for forever and to the right for forever. Is it approaching a value? And yes, this is, okay, even though it does cross it there in the middle. So now that's a little bit weird, but we have our horizontal asymptote and our 2 vertical asymptotes, right? That is it for this section, guys. I will see y'all in the next one. Bye.